So when we left off, we were talking about the results of density stratification and how that made the layers of the Earth. The Earth's atmosphere is actually, in large part, due to the same process. So density stratification was occurring, and the solid elements, but the most dense parts of the Earth went to the center. Well, the same can also be said about the least dense parts moving towards the surface. Gases are the least dense materials, and through various processes, including volcanism, most of the gases moved to the surface and became what we now call our atmosphere. The atmosphere was in large part water vapor, then carbon dioxide, hydrogen, sulfides, chlorides, things you would expect and associate with volcanism. Remember that the early Earth was very molten. There were a lot of eruptions going on. So this outgassing is the currently accepted theory for where the water vapor came from. We know this is true due to the fraction of oxygen 16 to oxygen 18, which you probably, hopefully, remember from chemistry class. But there were other theories about where we got our water vapor as well, including during that bombardment period, which we talked about with relation to the moon, that comets and such were hitting the Earth's surface. Comets are primarily asteroids that are covered with ice. So they would hit the Earth and liquefy, and then we would have that available water. But that one's currently out of favor. There are some issues with this density signatures of water that comes from comets. It doesn't really match the water we have around here. And it's important to note that the atmosphere that we had in the beginning was very, very different than the atmosphere we have now. Oxygen was completely absent from that early atmosphere and is now 21% of our current atmosphere. All right. So when that outgassed water vapor mixed into the atmosphere and moved away from the hot surface of the Earth in a very similar process it does today, that water vapor condensed, made clouds, and formed as rain. So the first permanent oceans formed 4 billion-ish years ago, not long after the Earth itself, 4.5 billion-ish years ago. But unlike that, our first oceans were fresh. It took longer for the salt that came from dissolution of rocks to collect in the oceans, quite a bit longer than it did actually for the oceans themselves to fall. And they were not a nice, the background picture. They were probably still large amounts of volcanism going on, so there was like lots of bubbling, boiling seas. Also, it was highly acidic, so all that rain that fell through the atmosphere had to fall through carbon dioxide of levels much higher than today, as well as sulfur, specifically sulfur dioxide, which when you mix sulfur dioxide with water, you get hydrogen sulfide, and that caused those early fresh oceans to be very acidic. When we get to chapter 5, you'll actually learn that the ocean is buffered in large part due to the salts that help make up its salinity. So there was also none of that really going on in the beginning, so very, very acidic. Over time, there was an equilibrium between the accumulation of salts due to the erosion of rocks running into the ocean and accumulating there, and their removal rate. You've probably stirred at some point too much salt into a glass just to see what would happen. Eventually, some of it falls out. So you would think that as the Earth continues to weather its surface, that the oceans would get saltier all the time, and that's not actually completely true. It's fairly static, stays the same. So we'll learn more about that in chapter 5. This is a diagram from your book where we have A, B, and C going on. So the first thing we have going on here in A is we have outgassing of volcanoes. Notice the lack of oceans. And then as the volcanic activity continues, we begin to get clouds that cause rain. Dude, that's the worst rain ever. And then over long enough periods of time, that rain would collect and form oceans. Meanwhile, at least that'll have even more forming. So this is just a visual of that outgassing leading to the oceans. This picture is not in your book. This is actually stromatolites, which I'll talk about in a second. So life's possible origins. We know that life likely originated on this Earth in the ocean. when we talk later on about the requirements for life, a lot of those things are a lot easier in liquids than they are in solid. It wasn't until, earliest life was about 3.5 billion years. We didn't get the first jump to land with the insects until well over 2 million years ago. So the very first life that we have fossilized records for, and something going back really far, are stromatolites. And stromatolites are the calcified remains of cyanobacteria. Cyanobacteria are photosynthetic. They're blue-green algae is another name for them. And this is actually stromatolites, modern ones. Right here in this picture, each little one, this little rock, is it's sort of like a coral reef. They leave behind a little calcareous shell and then more and more grow on them. So they're like mats of calcified algae. We actually have really, really ancient ones that are still fossilized in Canada. They found some of the oldest rocks known to man with these fossils of life in them in the Canadian Rockies, where there's very little volcanism going on. And we can figure out a lot about Earth's atmosphere by studying those fossils, because there isn't any direct evidence of the early Earth left anymore, because it's all been, the entire early atmosphere has been replaced by the gases of our modern atmosphere, particularly oxygen. And there's also, we can't go back in time yet. And there's also no crustal rocks left from that very, very, 4.5 billion years ago, because the very process of cooling and reforming destroyed everything. So oxygen, we take it for granted. All animals require oxygen. Actually, believe it or not, plants require oxygen to respire, but we always focus on the animals. And we think of oxygen as being a relatively benign molecule. We need it. One of the reasons why oxygen is so necessary for most life as we know it is because it gives so much energy in the process of respiration. But before that, that's a very complicated process to evolve over time, and we'll talk about that more in the next video. But oxygen can be fairly toxic, and it's highly likely that in the early Earth there was no oxygen. And we know this because very simple molecules like amino acids and things that we think must have had some sort of origins in the ocean, in the presence of free oxygen, those things rip apart. You've probably heard in videos or commercials about free radicals and how you have to take things, or oxidation. These are all processes where oxygen rips molecules apart. And because of that, it would have had a disastrous effect on early life. There are literally organisms, the anaerobic ones, that cannot live in the presence of oxygen. So, additionally, oxygen in our atmosphere forms ozone. Now, ozone, I'm sure you've heard of in the form of the ozone layer. Ozone is well, again, very reactive. Only exists, it's so reactive that the only place it exists normally in any great amounts is the upper atmosphere, where nothing will react with it. But when you have ozone in the upper atmosphere, it filters out a large amount of the radiation that is coming through from the sun, and protects things that exist at the surface of the ocean or on land. But at the same rate that radiation that we now find so dangerous, lack of ozone layers, increasing skin cancer, that lack of ozone may have spurred mutation. So that all that radiation can cause cells to mutate, or even molecules to mutate, which in the presence of all the goodies going on in the early ocean may have helped give the jump start to life. So this is a very famous experiment. Stanley Miller worked for this guy named Harold Urey. This was his thesis when he was a college student, or I guess grad student. And what he basically did was he took the molecules that we suspect made up the early atmosphere, things like ammonia, methane, carbon dioxide, and hydrogen, things that are commonly associated with volcanic eruptions. And he put them in sort of a broth. He took simulated ocean water, salty water, and he both heated it so that, there was all the things were moving around. And he also exposed it to sparks of electricity. You can actually kind of see them right here. It looks like one of those globes Mr. V has, that kind of spark when you touch it. This was supposed to simulate lightning. So in an early atmosphere where we have all that condensing of water vapor and all that heat, we would potentially have a whole lot of storms. And what would happen was that in the presence of heat, the seawater, and these molecules, the carbon dioxide, methane, and the ammonia, that he actually got organic molecules, complicated ones, many chains long. And the idea is that we think that in the early oceans there was sort of this goop right at the surface where things tend to float, where it was acted upon by radiation and lightning, and where it's possible that having all of this stuff together sparked life. So that's kind of the idea of where life came from. And we're talking wildly, wildly primitive life. Things that are just a few strands of DNA that's able to replicate itself. So we believe that that idea is supported by Stanley Miller's experiment. I'm actually going to come back to evolution and natural selection in the next video.